Today we will cover internal forces. We will talk a little bit about moment, shear, and then diagrams. Even though I didn't have here an example about the end forces or end diagrams, these will be the forces which pull or push our cross-section. So internal forces arise when a structure resists external loads. So what is external load? External load, we have, for instance, live load on the bridge due to trucks or cars. Then we have live load on a pedestrian bridge due to pedestrians. Then we have snow, we have wind, earthquake, etc. So all of these belong to external load. We have three main forces. Internal forces, we have normal axial force, which will push or pulls along the length. So it is given in the picture here. Then we have shear force, which will act perpendicular to the axis. And we have bending moment, which will cause the bending. So what is shear force? It's the internal force parallel to the cross-section that tries to slide one part of the beam over the other. What is moment? That is the internal bending effect at a point due to external forces, and it causes the beam to bend. Just review, in a pin support, we have moment to be equal to 0. Shear force is different than 0. Normal force is also different than 0. In roller support, we have moment to be equal to 0, but shear is different than 0. And in fixed support, we have moment and shear and normal force to be all of them different than 0. So this is just a review, because once when you start to draw the diagrams, you need to recognize that at pin and a roller support, our moment will be 0. So if we have, for instance, some simply supported beam subjected to two P forces, so P force is external load, and the distance from pin support or roller will be L third. So firstly, and this is your reminder, you need to draw free body diagram. In this free body diagram, you will have vertical force A, then you will have horizontal force AJ, two external forces, and one force in roller. After that, we are writing equations of equilibrium. So we have sum of forces in x direction to be equal to 0, which will give us HA to be equal to 0. Then we have sum of forces in y direction to be equal to 0. So A plus B is equal to P, and we have sum of moment at A or even at point B to be equal to 0. I here did sum of moment at point A to be equal to 0. You will have roller force B times L minus first force P times L over 3 and minus force P times 2L over 3 to be equal to 0. Using that equation, you will determine that your reaction at B is equal to P, and using the second equation where sum of forces in y direction is equal to 0, you will determine that A is equal to P. So these were our reactions and supports. So this is the first step. The second step will be to determine the internal forces in each relevant point in along the beam. So sign convention. So we have shear force. If you are cutting from the left, your positive will be vertical up. If you are cutting from the right side, your shear will be vertical down, or shear force tend to slide cross section. Regarding to moment, if moment is at, from the left side, it is along the clockwise, we say that that one is positive. And if you are cutting from the right side, we have counterclockwise moment to be positive, or we tend to it tends to bend the cross section, where the top fiber will decrease in length and the bottom fiber will increase in length. After that, these are our sign convention. We have a shear force at point A. So what you see in point A when you cut the beam. If you are cutting the beam at the support, you don't see anything else that your force P. So your shear at point A is equal to P. Similar situation for the roller B. Your shear force at point B is equal to B, which in this case we are cutting from the right side. Your positive shear will go down and your reaction at support B is going up. So that means that your shear at point B is minus P. If we are cutting at point 1, we will have two values of shear at point 1, one which will be from the left if we are cutting very close to the force but from the left side, and the other one if we are cutting very close to the force but behind the force. In first case, you don't see anything else except the reaction at point A. That means that your shear at point 1 left will be equal to P. Your shear at point 1 right side, you will have reaction at support P, which is positive, and we need to take in account the force P, which in this case will be P minus P is equal to 0. So the same situation for the point 2. So we have V2 right and V2 left, again to be reaction at support B will be your V2 right, which is equal to minus P. And if we have the shear at point 2 but behind the force, then you will have a 0. Your moment at point 1 will be your reaction at support times L over 3. So that means that your moment is P times L over 3. And it will be positive moment because it tends to bend a cross section that the top fiber will decrease in length. M2 will be again B times L over 3, which in this case is equal P times L over 3. So this is the explanation how to determine the shear force at point 2, right and left, and how to determine the moment at point 2. Then we have to draw. So what we know? We know for sure that at point A, that is what we determined, our shear is P. Then we have at point 1 left, you have again the shear force to be equal to P. Behind the force, it will be 0. So we are drawing P at point A and we are drawing P at point 1. We just connect them, and that is the first part of our shear diagram. From the other side, we have the same. At point B, we said that we have a negative shear minus P, and we have at point 2 right again minus P. That is the only thing which you see from the other side, and behind the force we have 0. So your shear diagram will be something like this. Regarding to the moment diagram, we determine that at pin support and in a roller we don't have any moment, which means I have 0. But at point 1 and point 2, I will have P times L over 3. And from the other side, for a point 2, again, I have P over times L over 3. And I wanted to check my diagram. I determined what will be the moment at point 3. At point 3, which is in the middle of the beam, you will have reaction at A times L half and minus force P, but now the distance will be L over 6. When you solve this, you will obtain that your moment at point 3 is also PL over 3. So this is one example how to draw the diagram. I did one more example where I have again pin and roller support, but this beam is subjected to point force 10 kilonewton, one moment of 15 kilonewton meter, and I put uniformly distributed load of 2 kilonewton per meter. The distances will be 2, 3, 3, and 2. Again, first step, free body diagram. So we have at pin support AJ, we have A, at roller we have B, then we have 1.4 force 10 kilonewton, 15 kilonewton meter, and from distributed load we will have a point force which will be 2 times 2, and in this case that is 4 kilonewton. Next step, we are writing equations of equilibrium. So sum of forces in x direction is equal to 0. You have AJ to be equal to 0. Then we have sum of forces in y direction to be equal to 0. We have A plus B minus 10 minus 4, which in this case is equal A plus B is equal 14. And you could pick sum of moment at point A or point B to be equal to 0. I did sum of moment at point A to be equal to 0. So we will have reaction from the roller B times 10 minus 4 Q force times the distance, which in this case will be 9, minus moment, which is 15 kilonewton meter, and minus 10 times 2 from the force, which is minus 20. Solving this equation, you will get that your reaction B is equal 7.1 kilonewton. Plugging that into the second equation, where sum of forces is equal to 0, your reaction at A will be 6.9 kilonewton. So this will be the steps which you have to do immediately in order to determine the reactions at supports. After that, so we have all of these. We have, we determine reaction at A, we determine reaction at B. Now we have to determine the internal forces. So what I suggest, so we said if we are cutting from the left side, your shear is positive if it goes up. So we have, if we are cutting at point 1, we forget about the rest of the beam. What we have reaction at A, which is 6.9, and that is your first shear. VA is equal 6.9 kilonewton. That is the only thing which you see. Moment at point A, since that it is a pin, has to be equal to 0. After that, at point 1, you see only reaction 6.9, and we have point a force of 10 kilonewton. Firstly, we have to determine shear force left from the force. So you don't see anything else except your reaction at point A, which is 6.9 kilonewton. The shear force 1 to the right, you see both forces, 6.9 minus 10, which in this case is minus 3.1 kilonewton. Your moment at point 1 is 6.9 times 2, which is 13.8 kilonewton meter. This is the shear and moment at point 1. Then we are going to the next point, which is point 2. So we have reaction at support A, 6.9. Point force at point 1 is 10. Then we have point 2 subjected to a moment of 15 kilonewton meter. Now you have to determine your shear at point 2. What we see is 6.9 from the A minus point force of 10, which is again minus 3.1 kilonewton. But regarding to the point 2 and moment, we will have left and right side. Left, where we will not include the moment, and right side, where we have to include the moment. Moment at 2 left will be ours, 6.9 times 5. I made a mistake here. It's 5 minus 10.3, and then we will get a little bit different value what I get here. I have 11.4 kilonewton meters, so which is wrong. And we have M2 right, so this M2L plus, we have to take in account moment of 15, which is 26.4 kilonewton meter. So this is the moment which we obtain at point 2. Please check the calculation because I put instead of 5 the distance 6. So here you will have some differences in the calculation or the numbers, but the procedure will be the same. I don't want to go and to redo the problem. Regarding to the point 3, Now it is easier to cut from the right side. Why? Because you have less variables here. You will have roller support 7.1 kilonewton, and you have distributed load of 2 kilonewton per meter. So what we have at point 3, we have 4, which is coming from distributed load, which is our force Q, 2 times 2, which is 4, and minus 7.1 will give you minus 3.1 kilonewton. Your shear at point B is also minus 7.1 kilonewton. Why? Because your vertical force is going up, and we said shear force tend to slide, so it has to go down to be positive, so VB is minus 7.1. What is our moment at point 3? That is 7.1 force from the roller support times 2, the distance, minus Q, which is 4 times 1, and that will give us 10.2 kilonewton meter, and moment at point B is equal to 0. Now we have to draw the moment and shear diagram. So we have all internal forces already determined. Firstly, we can do the shear force diagram. So at point A, we have 6.9. At point 1 left, we have 6.9. We connect the 2 points, and that will be our first part of the diagram. At point 1 right, we have minus 3.1, so we are going in a negative part of the diagram. At point 3, we have also minus 3.1. We connect the first and the third point, and that is that part of the shear diagram. And at point B, we have minus 7.1. We connect 3.1 and 7.1, and we are done with shear. Regarding to the moment diagram, we have at point A 0, at point B 0. We calculated moment at point 1 to be 13.8. We connect 0 with 13.8, and we are done with the first point. The second point, we have M2L to be 11.4, so we are connecting 13.8 with 11.4. Then we have M2 right, which is 26.9, 26.4. So we have to increase the value up to 26.4. The next point is M at point 3, which is 10.2. We connect 26.4 with 10.2, and we are done with the point 3. At the end, we have a 0, so we can connect 10.2 with a 0. In this part where we have a distributed load, we need to add parabolic section in positive direction, which is QL squared over 8, and Q in our case is 2 times 4 over 8. It will be 1, and we are done with moment and shear diagrams. We couldn't draw anything regarding to normal forces because we don't have any load in x direction, so our normal force diagram will be 0.